Over the course of my studies in theoretical physics, I've traveled across the continent and around the world sampling new ideas and tasting different answers to the questions of how and of why. And still, I find there remains a deep hunger which lives within me, a burning desire to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my Titanium Physicists. You're listening to the Titanium Physicists Podcast, and I'm Ben Tippett. And now, allez, physique! In 1998, Saul Perlmutter and 31 associates from the Supernova Cosmology Project published a paper which changed the way physicists think about the universe. By looking at the color and the brightness of photons emitted by standard candles called Type 1a supernova, they could determine not just the distance these photons travel to reach us, but how the rate of the expansion of the universe has changed over its history. Their results were astounding. Firstly, our universe is not only expanding, but the rate at which it's expanding is accelerating. Second, in terms of gravitational influence, the matter causing the acceleration should make up about 73% of the matter in the universe. So prior to these findings, physicists had always expected the universe to either recollapse under its own weight, or for the expansion to slow forever as the matter in the universe became more and more rarefied. The discovery made by Perlmutter and his collaborators indicate that the universe must be full of a type of matter that doesn't rarefy as it's stretched out, a matter we call dark energy. This discovery led to the award of the 2011 Nobel Prize in Physics. Now, no one knows much about dark energy. Orthodox general relativity assumes that it's a non-zero cosmological constant, of Einstein's biggest blunder fame. But other sources have been proposed, including the one we'll be talking about today, a type of matter called phantom energy. Just as the only thing worse than being in a dark room is being in a dark room full of ghosts, phantom energy is the worst of all types of dark energies. If phantom energy is indeed the source of the cosmological acceleration of the universe, then Einstein's theory of general relativity predicts a grisly end to us all, a big rip, where runaway acceleration of the universe will tear us all to pieces. Alright, so today on the Titanium Physicists Podcast, I have a guest, Ryan North.
Hi.
He's the author of Dinosaur Comics at Quants.com, and he has a new book out, Dinosaur Comics. Everybody knows failure is just success rounded down. How's it going, Ryan?
Good. How are you?
Are you having a good night?
I am. I just walked my dog.
Alright. So, Ryan, for today, I've assembled two of my best titanium physicists. Arise, Dr. David Tsang!
I rise from my grave.
Dr. Dave, he did his undergraduate at UBC with me, his PhD and master's at Cornell. He's currently in Caltech, working as a postdoc astrophysicist. And now, arise, Dr. Jocelyn Read! Dr. Jocelyn did her undergraduate at UBC. And her PhD at Wisconsin-Milwaukee.
And I'm very scary.
Yeah. She's currently at the University of Mississippi working on neutron stars. Alright, guys. Let's start talking about big rips.
So before we start, I just want to make it clear that I'm the only non-doctor here, right?
You could be a doctor.
There are many people that don't consider physicists real doctors either, so...
Well, I do.
Yay!
Sweet.
That's something.
I could write you a prescription.
For physics?
For pain. So, Dave, tell Ryan about the expanding cosmology, would you?
Tell the non-doctor,
Well, non-doctor.
but use little words.
So you know that light travels with a constant speed, right?
Yes.
So,
regardless
Einstein's
of observer speed.
That's right. So based on how long light takes to travel, or how long light takes to get to us, we can figure out how far something away from us is.
Yeah.
And Edwin Hubble, way back when, found out that galaxies that are further away from us tend to be moving faster than the galaxies that are closer to us.
Faster away from us or faster
away from us.
Okay.
Everything, in all directions, the galaxies were moving away from us. And what physicists decided from this was that this implied that the universe was expanding, and even backtrace to figure out that the universe must have come from a Big Bang. And
So, I don't want to interrupt you, but I am absolutely going to interrupt you right there.
absolutely.
Everything's expanding away from us. That doesn't necessarily mean we're at the center of the universe, right? It's sort of like we're on the skin of a balloon, and that's
right.
expanding, so everything's moving away from us.
A good way to think about it is that we're inside a muffin or a cake, and that the whole thing is expanding out. So at any point inside that muffin, that delicious, delicious muffin, other points are moving away from you as the whole thing sort of gets bigger.
Other chocolate chips in the muffin.
Yeah, right.
I feel like my balloon analogy was just as good, but didn't have chocolate chips in it.
Well, we're...
That was its main failing.
Yeah, exactly. Balloons aren't as delicious, trust me.
Oh, I don't have to take your word for it.
It's just sort of easier to imagine yourself in the middle of an expanding muffin than on the surface of a balloon, since we usually do think in 3 dimensions.
Okay. All right,
Also,
so...
muffins are delicious.
Yes. So, sorry to interrupt you, David.
No problem.
We're
Interrupt
in the expanding
more.
universe, and
Yes.
and shit's about to go foul.
So the universe is expanding. We knew this from Hubble. What Saul Perlmutter and Adam Rees and the other people that won the Nobel Prize recently found out is by looking at supernovae exploding, they found that the universe is actually not only expanding, but also that expansion is accelerating.
Right.
And I mean, before they figured this out, we thought that the universe was either closed or flat. So the universe was going to collapse back in on itself, or that it would just keep coasting forever.
There's
So
no
that-
middle ground where it sort of slows down and stops, and we're good.
Right. Well, it doesn't really stop.
That's kind of the coasting forever one.
Right.
Right.
So you can imagine throwing baseballs. Like if you threw a baseball straight up, it would either come all the way back down, but if you threw it with exactly the escape energy, it would just sort of trail off to infinity forever.
Yeah.
The escape
So-
energy of the gravity of Earth, you mean?
Right.
Right.
Yeah. Well, I mean, this is me throwing a baseball. It's going to go pretty far.
Yeah.
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 Yeah. Yeah.
And so instead, you have the Big Bang launching you against the gravity of everything in the universe.
Okay, I'm with you.
Right.
Which, if you're thinking about regular mass, that wants to fall back down, or, contract back in on itself.
Right. So instead of having a contraction, then maybe another Big Bang, another contraction, we've got an endlessly expanding universe.
And that expansion is accelerating faster and faster.
Yeah, so
Which seems
this is
crazy.
like we threw a baseball, and it didn't just sort of arc, but it actually went for a while and then started going up faster into the sky.
So it sounds like something's wrong with that baseball.
Something's wrong
Yeah.
with the muffin that we're
Yes.
in. That it's getting bigger.
So this
and bigger.
muffin just keeps growing and growing and growing.
Right.
And we're the little sprinkles in that muffin. We're the delicious baryonic sprinkles.
Right.
And we just keep moving further and further apart from everything. That's the regular picture of dark energy.
We mentioned phantom energy before. Dark energy has the quality that as you stretch it out, it keeps making this muffin larger and larger at an accelerating pace. But phantom energy kind of has a unique characteristic. So regular energy, the more you stretch it out, you imagine a thing full of toffee held between 2 or 3 people, and as they stretch it, it gets thinner and thinner.
Right.
Phantom energy has negative pressure, and what that means is the more you push on it, or in this case, the more you pull on it, the more of it there is. So somehow, it's becoming thicker and denser and gravitationally more powerful the more you stretch it out.
So regular matter would just get thinner as you stretch it, whereas something like a cosmological constant stays the same as you stretch it. And
Constant.
yeah, so it stays at the constant density no matter how much you stretch it. Whereas the main difference with phantom energy is it gets even more powerful as you pull it apart.
Right, so we've got normal matter I'm used to, where you stretch it against center. We've got magic constant matter, where you stretch it and you still at the same thickness. And then you've got double magic ghost matter, where you stretch it and you end up with more mass than when you started, or the same larger thickness.
Yes. But we also have to keep in mind that the difference with the dark energy and the phantom energy is that they are doing the opposite of what normal matter does, which normal matter will pull things to it, and then the cosmological constant or the phantom energy pushes stuff apart.
It's kind of like love in a valediction forbidding morning. That's right, I got John Donne up in your face.
So just so I'm not lost, these two types. The cosmological constant you're referring to, I always thought of that as a number, but it sounds like it's a type of matter in this situation.
It's the energy of empty space.
Okay. And this phantom energy, I take it no one has ever observed this energy, and we're just assuming it exists because it makes the numbers fall out properly?
Okay. The point of this whole thing that Ben set us off to investigate, it was this paper saying, we always look at something between no dark energy and cosmological constant dark energy, and all the measurements are kind of converging towards this cosmological constant dark energy. But you can actually go further in the past the cosmological constant into this phantom energy, and there's a region of that that's also allowed by the current measurements.
Okay, so this might not exist, but if it does, this is what it would behave like.
Yeah. So, in essence, it's like when the field theorists saw this behavior, this accelerating expansion of the universe, they said, well, there's two possibilities for it. One possibility is it's a type of matter, like an anti-gravity matter, but the more you stretch it, the thinner it gets. And the second said, the more it's a type of anti-gravity force that the more you stretch it, it stays the same width. And then these ghost energy guys, your phantom energy guys came in and said, well, there's a third type of matter that we haven't considered, which is a type of matter that as you stretch it out, it gets, heavier.
Right. You're being very particular in distinguishing between phantom energy and ghost energy.
No one calls it ghost energy.
So you're reserving the right to invent or discover a ghost energy down the...
Yeah, I'll patent my special energy generating machine that will burn ghosts.
Perhaps trap them in a proton beam?
That's right. Put them in a big furnace afterwards, and, the oil crisis will be over.
Yay!
So I'm with you so far. We've got phantom energy that you stretch it and it gets thicker. Phantom matter, I guess.
Yeah, that's right.
We're selling energy, but it's matter, right?
Nobody knows what it is, so they call it energy because everything with mass is a type of energy, according to Einstein. Mass can be converted to energy, back and forth.
Right. Okay.
So they call it energy because it comes from the word dark energy, which referred to the fact that we don't know what type of energy is causing this accelerating expansion of the universe. And they called that dark energy to contrast with dark matter, which I don't want to get into now, but it's this other matter that we see gravitationally, but we can't observe optically, so we call it dark matter. So anyway, that's the hierarchy of names. That's why we call this stuff phantom energy specifically.
Okay.
So the deal with this is that phantom energy does more than just sit there as you stretch it out. Like it does more than just sit on your desk. It has a gravitational effect. And the gravitational effect, as we said before, is to cause expansion in the universe. So the more of it there is, the faster the expansion takes place. And so we end up with this kind of runaway expansion effect. So at first, the universe is expanding, and then suddenly the amount of phantom energy doubles, and then so the expansion goes twice as fast, and then the phantom energy quadruples as a result, and then the expansion quadruples its speed, and so on. And so you get this runaway cosmological expansion.
Right.
And so
what kind of time frame are we talking here?
35 billion years.
So our universe currently is 14 billion years old, and the effect of phantom energy can cause this thing called a big rip, which is the net result of this runaway expansion, about 35 billion years after the Big Bang, right?
Giga years.
So that's a billion years. So in other words, in about 14 billion years, we're going to stop seeing galaxies. Why?
No.
Yeah. Okay.
Wait. But that's going to happen without phantom energy. We should back up and talk about stopping seeing stuff in the regular situations before we go all crazy with the ghost. Well, okay, so we have the constant speed of light, and the universe started a finite time ago. So that already says there's only so far we can see out before we reach like the edge of how far light could have traveled since the universe began.
Right.
So that's the limitation on what we see right now is how how far away could light have started from us and then still reach us. Now, as the universe is expanding, if we go further and further in time, at some point we have that the universe is expanding out of the cone back in time of stuff we can see. So when I say cone, I've cut a slice through space, and I'm just considering one sort of slice through space, and I can see out to a circle.
Right.
And then going back in time, that circle gets bigger and bigger, so it makes a little cone coming up to the point where I am now.
So if a star moves farther away past this point where light will take the lifetime of the universe to reach us, then we can't see it anymore.
Right.
Okay, here's another way to think about it. The universe has this thing called a Hubble constant. Hubble, as Dave said, discovered that all of the galaxies in the universe were receding from us. The rate at which they're getting farther away from us is determined by the distance, right?
Okay.
So at some point, at some distance from us right now, there's an object where the distance between us and that far, far away galaxy is increasing at the speed of light. So it's increasing every second. 3 times 10 to the 8 meters are bubbled up between us and that distance, right?
Right.
So we can never ever see that galaxy.
That's right.
Because no matter how long we go along, our light cone is never going to be able to go back and see where that galaxy was, because that galaxy is going away at the speed of light.
Right. So
light's like a guy on a treadmill.
Well, yeah,
Right.
exactly. Yeah. So a photon trying to walk the distance between there and here will never arrive at the distance, because the treadmills gets pushing it back faster than it can move in this direction.
It's like a black hole.
It is. It's like
everywhere.
a black hole turned inside
outside
right?
of space.
Yeah.
Yeah.
We call this the cosmological horizon, right?
Right.
So the deal is that if an object, a galaxy, falls to that distance or behind it, it will get redshifted. It will turn dark, dark, dark red, and its spectrum will shift and get, the photons will end up losing an infinite amount of energy trying to make the trip. So once an object's past that, a distant galaxy, we won't be able to see it anymore. And as it crosses that,
Right.
it will fade from regular, yellowish light to reddish light to infrared to radio to, microwave radio, and then it'll fade away completely.
How long would this fade take? I guess it depends on how long it takes to cross this threshold.
Yeah, exactly. It depends.
And how fast the expansion is happening.
But it happens in a finite amount of time.
Right.
So in a finite amount of time, it will go from red to black and not being in there anymore, according to the person with the telescope trying to watch it.
Right.
And as Jocelyn said, our universe isn't old enough yet for us to see this happening. But if we wait a few more billion years, we'll be able to see this horizon.
Yeah. So hold your breath.
Hold your breath, and you'll see this curtain past which,
I think it's something like 9 or 10 billion years.
And then galaxies far away will slowly blink out.
So eventually it'll look like our galaxy is just sitting by itself, and we won't be able to see.
That's a really spooky image.
Right.
And people born then, like civilizations that arise then, won't have any clue that there's any other galaxies besides our own.
So, you're saying it's going to take 9, I think it was 9 gig years for it to start happening from where we are for us to notice it. In that time, is this like the sort of thing where within a generation you'd notice stars are missing, where they used to be there when Grandma was alive? Or is it, within the next several billion years, the stars start going out one by one until...
It would start with the furthest ones away.
And no one but astronomers would notice them with their super telescopes in space.
Yeah.
So,
and then if we're just doing like regular, boring old cosmological constant acceleration, it's most of the stars we see are in our galaxy. Well, pretty much everything we see. There's a few smudgy nearby galaxies you can see in the sky with binoculars, but most of what we see is in our
still
galaxy.
Within our galaxy cluster.
That would in the cosmological constant scenario, our galaxy stays bound to itself and just sort of floats along.
And our galaxy stays bound within our galaxy cluster, called the local group.
Right, that's true.
But we're not considering that. We're considering the phantom energy.
The crazy.
That's right. In this one specific scenario with this crazy phantom energy, this acceleration would ramp up so quickly that it would start... First, it would pull apart the very distant galaxies from us, so we wouldn't be able to see them. And then
the force increases. This sort of dark energy force pulling everything apart increases as time goes on until it is comparable to the force of gravity holding like a distant galaxy cluster together.
Right.
And that galaxy cluster can get pulled apart. Right. And the same thing can happen for a galaxy.
Yeah, so let's see. But I wanted to say something first.
Okay.
Sorry. Okay. So where is that? Yeah, one other way to think about this is if you can't see the light from something, if it's causally disconnected, there's no connection that's holding you together. So you're severed from any kind of communication with that other galaxy.
Yeah, and nothing anyone can do in that galaxy can ever affect me.
Exactly. Now, the crazy thing with the big rip, or this phantom energy, is that it keeps accelerating and accelerating more, so that it actually unbinds and disconnects the Milky Way from itself.
So eventually we wouldn't be able to see, the outer spiral arms or the middle of the Milky Way. All we'd be able to see is our little
solar system.
Yeah.
So and then it keeps going. It unbinds the solar system. It explodes the Earth. It disassociates every atom in your body.
Yeah.
And about 10 to the minus 19 seconds before the end of the universe, the atoms in your body would rip apart.
That's right. So let's draw a picture here. So Big Rip
It'd rip your face right off.
Big Rip minus 60 million years. Suddenly, the astronomers on Earth see all of the other stars in the solar system start to go out. Right? So we stop seeing the outer spiral arms, and we stop seeing the middle of the solar system. And this happens...
The galaxy.
Galaxy, Ben.
Yeah, in the galaxy, sorry. And then about 3 months before the Big Rip takes place, Pluto disappears.
Wait. This first scenario was how long before everybody dies?
60 million years.
Yeah,
then we jump to 3 months?
Yeah, the Milky Way is really big compared to the solar system.
That's right. So it takes...
Did you
have something better to do in those
No, but I guess I'm approaching this from the point of view of someone who likes the image, but this is a really spooky and terrifying picture of the stars going out one by one further away, and it's getting closer and closer and closer and closer.
Yes.
And it would be great if this could happen in like a 2-hour movie time frame, where maybe a ragtag group of heroes.
Well, you start with the Milky Way just getting pulled apart, and you see that happening, and you're like, oh shoot, I only have 60 million years, but you don't really care. But as soon as Pluto disappears, you have 3 months.
That's not even enough time to write like a NASA grant to get a shuttle to go blow something up on an asteroid. Even if
to be fair, the sun has already exploded by this point. But
well, we fixed it.
Yeah,
obviously.
Yeah, we fixed it.
Right, we sent Bruce Willis.
Right, to blow it up.
Yeah.
Think about it though. That's a pretty good last 3 months in the universe scenario. And that's a lot of debauchery that can. Yeah.
And this is the same no matter where you are in the universe, right? If you're on a planet somewhere, you've got 3 months from the point of anything, at the same distance that Pluto is from where you are.
Exactly.
It's more about the gravitational binding energy.
So if we're writing this story, every sentient species in the universe has 3 months to figure this out, and they're all now alone.
That's right.
Yes. They've been alone for millions of years.
Jocelyn. They're sad.
Yeah.
They're terrified and alone, and they've got 3 months to figure something out.
Okay.
Come on, party!
So, half an hour before the Big Rip...
Whoa. What happened to our 3 months?
Okay, so 3 months
We just sat around?
Yeah.
No, that's the debauchery, remember?
Yeah.
Oh, right.
I can't go over 3 months.
You don't have to worry about any babies.
I get hungry.
Listen, eating sandwiches and taking naps is its own type of debauchery.
Food is an important part of enjoying yourself at the end of the world.
So over the course of 3 months, if you're on Earth, and it's like it was now for some reason, you're watching the planets blink out.
They're suddenly shooting away from you, and you can't see them anymore.
Yeah.
Right.
They redshift away from you.
Black. Jupiter will go black, and then Mars will go black, and then
we'll get
still got
pulled
the sun.
away from the sun.
Yeah, the sun will go black. Right.
But then we're dead, right? Like we're frozen.
Well,
Well, we already fixed it once. We can probably make some mini suns on the Earth.
All right, so we plug in the space heaters.
Well, you need a space heater because that's all that's left. You in space.
Wow.
We've probably got enough collected enough energy by this point that we can at least survive for the 3 months that
On batteries.
yeah.
Okay, so we're at half an hour.
Half an hour, and you get pulled off the Earth.
The Earth just
The
rips
Earth
off.
explodes.
That's right. You get sucked off the surface in the Earth, and you find yourself floating in a void.
Now is this
As opposed to the 3 months
painful?
before where you were just sucked off.
Is this painful? Like, am I being sucked off as in I'm being torn to pieces, or just like
It's not
the
the
gravity of
pleasurable
the
type
planet
of
has been
sucking.
neutralized and I'm now sort of just floating around in space, which is kind of cool.
You've just sort of watched everything get... there must be some tidal forces, actually, at this point. The length scales of the expansion.
No, there are no tidal forces.
Really?
Yeah, because it's a.
It's just
uniform.
unbound.
Because the space
Uniform.
time in these models is really uniform, so there's no tidal forces.
Okay.
But basically, just the gravity stops being able to hold the Earth together. So it
That's
just
So over these 3 months, my perceived weight is going down.
yes.
Right.
Sweet. So we're being able to jump further and further and further because the Earth's having less and less effective gravity because there's something outside pulling us away from it with more and more.
But it's not outside pulling us away. It's everywhere
It's inside
at once
you.
expanding. So that's why I'm saying if we're at the point where the Earth's exploding,
Yes.
there's probably some noticeable effects, even on a human scale.
Like I would be uncomfortable. I'd be sort of pulled.
Yeah, you'd feel kind of like
Be stretched out with the
it's
force
like a
of
really
G.
good chiropractor.
You'd be like sort of puffing out with the force of a G, but your body can still hold itself together in that case.
Oh yeah.
So this is the half-hour point where I'm
Floating in space with a helmet on, maybe.
a force of a G pulling me in every direction.
Yes.
And hopefully my eyeballs haven't popped.
You've got a helmet
right.
on, say.
Yeah, obviously.
But the helmet is getting
It's the
pulled in every
future.
direction.
Right, and suddenly
The helmet doesn't protect you.
you notice all these electrons flying around, and your atoms start unbinding.
Go on. Sounds survivable.
Well, first you'll get pulled to pieces, right?
Right, your face will get ripped off.
Right. Far before your electrons. Well, I don't know how you're held
No, it's
together
about
with
the
like
same. About the
valence
same, yeah.
bonds, right?
Yeah.
Yeah.
A valence bond is stronger than like the.
Right. So your face will come apart before the atoms do.
Yes, but only briefly
Yes.
before the atoms.
Only briefly, very briefly.
And then.
Well, we're in the last sort of.
We're in the last
This is
10
somewhere between what is it? Somewhere between 30 minutes and 10 to the negative 19 seconds.
your atoms start pulling themselves apart.
Right.
And
But
then,
I'm dead before that point.
if you're lucky.
Well, I don't know. You're a future person on this rebuilt Milky Way or rebuilt solar system. Who knows what you can do?
Also, French ghosts are pulling you apart, so.
When are they French?
Well, they're phantoms.
Why are they French?
You guys have been out of Canada too long.
Why?
I still don't get it.
It's the French word for ghosts.
But it's also the English word for phantom.
What other type
And-
of phantoms
and
are there
if
but
it's-
ghosts? There's opera phantoms and.
That's true. It could be energy of the Phantom of the Opera, the music of the night, if you will.
So my atoms are being pulled apart,
That's right.
which would release a tremendous amount of energy, would it not?
The energy.
Well, there's that much energy
It's small.
everywhere.
It's small compared to the amount of energy that's pulling you apart.
Right, but it's still something to be pretty proud of.
Yeah. you did let loose a pretty good rip.
atoms.
It's something.
Then 35 billion years from now, that would basically every single subatomic particle would be separated from every single other subatomic particle.
and nothing else could
It's only
exist.
20 billion years from now.
It's 20 billion.
Oh,
Dave.
sorry, 20 billion years. I'm sorry. 20 giga years. Or giga years if you're Doc Brown.
Yeah.
And then it just disperses until we have a bunch of undifferentiated low-level energy floating in an empty void.
Well, there must be some sort of weird, like, string theory, quantum gravity kind of things happening in the ultimate moments.
Well, if memory serves, you end up with each point in the universe right now becomes infinitely large a few months later. But not
So
really
it's-
a big bang. It's just the phantom energy universe keeps on going on past that. There's no singularity that ends it. It's just that past the big rip, nothing with any width can exist.
Being wide is pretty much all that I do.
I know. I've been practicing a lot lately. I don't know what the deal is.
So this is a pretty depressing ending
Or awesome.
It's only for this one specific case, though.
Yeah.
And even the times we're giving are only for one particular realization of this phantom energy.
Yeah.
But
It
it's
could
still
take like
accelerating,
40
right?
gig years.
Or
It is accelerating.
Yeah.
So even after
We do expect the galaxies to start winking out at some point.
But they won't blow up. It's unlikely that they will blow apart based on current measurements of...
you start with they won't, then you correct it up and say, well, it's unlikely.
We have some error in the
That's
measurements.
science.
Don't come
Science
trying to
cannot
make-
guarantee your survival.
That's right. I think you should take consolation, Ryan, in the fact that your enemies will also be ripped to shreds.
Well, I've got 30 gig years to ensure that. Our ragtag group of heroes didn't stop this.
No, there's no way to stop it. Phantoms always win.
It's a great image. I think the image of watching the stars blink out is nice, and since we have this time frame where it accelerates, and you could have a generation where, in that 3-month period before it gets really bad, you've got maybe a generation, 40 years, where it's noticeably getting worse.
Yes.
And I think that's really cool.
Still close by stars start winking or start accelerating, redshifting away from us.
Yeah, and you have a lonelier night sky every evening. That's creepy. That's like really creepy.
You can wish upon a star, and then it will go away, and then your wish won't come true, right?
We're like, oh, nuts. It's impossible to affect that star, nor can it affect me.
That's right. Good. Any other questions, Ryan?
No, I think this was covered in an awesome yet depressing way.
That's about our
Yay!
half hour.
Were you scared? Did you pee yourself?
I did. It's not scary because I have to face reality, and I will probably not be around to see it. But
Quitter.
it is, but it's a really great image, and I think there's something you could do with that. Sort of have fun with it if you were going to tell a story or do something with it.
Awesome. All right. Well, that's about our half an hour. So thanks, Dave and Jocelyn. Your efforts have pleased me. They've borne fruit, your efforts have, and that fruit is sweet. I'd like to thank my guest, Ryan North. Everybody go to his website and buy some t-shirts and buy his book. Everybody knows failure is just success rounded down. You can email us at barn@titaniumphysics.com, or you can follow us at Twitter at @titaniumphysics. You can visit our website at www.titaniumphysics.com, or look for us on Facebook. If you've got any question you'd like my titanium physicist to address, email them to TIPHYTER, TIE Fighter, at titaniumphysics.com.
That wasn't taken?
And if you are a physicist and you'd like to become one of my titanium physicists, email physics@titaniumphysics.com. We're always recruiting. The Titanium Physics Podcast is a member of Brachylope Media. If you enjoyed the show, you might also enjoy Science Sort Of or the Weekly Wienersmith. Check them out. The intro music is by Ted Leo and the Pharmacists, and the end music is by John Vanderslice. Good day, my friends, and remember to always keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet, jumped through a window